Good afternoon. This is David Eastwood, Geotech Engineering and Testing. I'm here to talk to you guys about geoforensic evaluation of a building we worked on in Houston. We had a team work on this project. It was Dr. James Wang and Dr. James Namekar and me kind of all put our heads together and work on this project together. Last year sometimes. The project basically located is in Houston. It's a big metal building, about a couple 100,000 square foot, and you can see the pictures of the exterior in some areas. Um, Close-up picture of the northwest side of the building. Okay, this is the southeast part of the building, which a portion of the presentation, I have a few slides missing. Um Basically, I'm with Geotech Engineering and Testing, and we've been around for about 39 years. We do geotechnical, environmental, material testing, and geoforensic engineering. We have our own rigs, and we can get on the projects quickly. We have about 60 people all over Houston. Uh, we have about 181 people RSVP for this presentation. Most of the people that making the presentation are civil engineers, a lot of structural engineers from all over Texas, a lot of people from various cities around the Texas, and so kind of a variable audience we got on this project. I have some information about my contact information. If you need to reach me, my phone number is 713-699-4000. And of course, my email is de@geotecheng.com. Anyway, this is the building, southeast of the building. That's the north side of the building, northwest. And you see a big metal building. Project timeline. The agenda today is project timeline, site visit, field exploration, results of laboratory tests, engineering analysis, reasons for foundation distress, repair techniques, and recommendations for additional studies for this project. The owner came up to us on this project and told us, hey, we got a building, the floor slab is all cracked up, and we're going to have problems operating on this floor slabs, what caused it, and how to fix it. So we went out there and looked at the paperwork on the project. September 11, 2020, they did architectural drawing. The civil drawings came out in 21, May. August, the specifications for the construction of manufacturing was put together. January 22, started construction. That's important. In 22, they started. It was kind of a drought year. They didn't have that much rain. Uh, July 22, structural drawings were completed, and construction completed in August of 2023. February 26, Geotech Engineering and Testing was engaged to work on the project. With a bunch of site visits out there looking at the building, these red areas shows areas of the distress. They're just distress all over the place. You look at it. You look at the inside the building. It's a big industrial building, and you know, control joints in the floor slabs supposed to be on this project. Specs were maximum of 20 feet. We measured in a lot of locations joint spacing of 25 feet, and of course the higher the more the higher the spacing of the control joints, the more potential for floor slab cracking. And here in this one here is about 20 feet. There was a lot of loads out there on the floor slabs. These are heavy stuff. They're filled with rock, kind of sitting on the floor slabs. They have a contact pressure of about 600 psf. We calculate the settlement. It was not that heavy. A lot of floor slabs cracking. I mean, you go through the whole floor slab areas and you can see cracks all over the place. And you can see just cracks just throughout the whole floor slab areas. Crack, crack, crack. All the way from hairline to about 0.1 inch. And essentially, this thing was like 2 years old and just kind of falling apart. Control depth, control joint depth was 0.25 inches. As we know, the control joint depth should be 1/4 of the floor slab thickness. The slab here was 7 inches, so it should be more than 1.5 inches, the depth of the control joint, but it was only 0.25 inches. And you can see more floor slab cracks, separations in the near the oven, 0.75 inches in the control joints. Control joint again opening up, 0.25 inches. Control joints, 0.25 inches. More cracks. Control joints, 24 inches. The specs call for maximum of 20 feet. Now, ACI's got specs on the control joints on industrial buildings, and I'm going to talk about that in a minute. More cracks, more separations of the control joints, more cracks. Here's a press machine they had on that project. This press machine was subject to vibration. And one of the things that the contractor was saying that the vibration could have caused concrete cracking throughout the whole 200,000 square foot building, which is not true. So we monitored this, trying to see if this press machine, the vibration of it is causing concrete cracking. Looking at the foundation system for the control machine, for the press machine, it's basically sitting on a concrete mat foundation with a having a foam rubber in between its foundation and the rest of the foundation of the building to increase damping of the vibration. So that's kind of like an isolation joints and damping material. Also, they had a oven on the project, and the oven had a basement. You had to go in there. It was hot in there, and all the walls were leaking. You go inside. Look at the walls, and all the water is leaking. The basement. The walls, the water was just leaking inside the floor slabs. So they also had a Simco CMAC machine that cut off the marbles and stuff like that in the building that had a little bit of vibration, not much. The foundation system for this whole big building consisted of drill piers. Drill piers were 11 feet below the existing grade. Of course, they raised the site a couple of feet, so it was like 13 feet deep. The piers were basically 12 inches in diameter, 3 feet in diameter, all the way down to about 28 inches by 7 foot in diameter. They were good size drill piers. And then the slab itself, which is critical here, was supposed to be 7 inches with number 4 at 15-inch spacing, reinforcing in the floor slab areas. And here it says in the spec, building placed control joints at maximum of 20 feet. And of course, we measured at many locations that the control joints were measured more than 20 feet. So we went out there, did some investigation of the floor slabs. We all did some drilling, sampling. We did ground penetrating radar, GPR. We did macro elevations. We did vibration monitoring with geophones. We're putting piezometers in there to see where's the water in the underneath the floor slabs, and we did the crack survey. So when we did our borings on the building, we did 4 borings, 25 foot in the exterior of buildings, and 8 borings inside the building to a depth of 20 feet or where we can get it. We also did GPR inside the building at 8 locations to identify the concrete thickness and rebar layout. And then we did piezometers, 2 of them inside the building. The exterior borings, we had our own rigs going out there doing borings and trying to get samples of the soils with the building. The soils under the building were mostly sandy clay, lean clay type material. They were good. They were good soils, non-expansive, with low PI soils. We checked the water level with the tape measure and the weight at the end of it. There was no water all the way down to 20 feet. With the GPR, it's a device. We use the GPR a lot in forensics. Basically, it uses it. We use it for evaluation of presence of underground utilities, damage prevention. If there is any problem with any kind of a pipes underneath the building. GPR uses basically an antenna that transmits electromagnetic energy, similar to a cell phone. A receiver is located within the antenna and takes the reflected signal as it encounters, and with the soils with 2 different dielectric values. So GPR was used at 8 locations. Basically, the purpose of it was to identify underground utilities. Also, we wanted to know the thickness of the concrete floor slab and rebar layouts. So also, we did it throughout the whole building to see if there is voids underneath the floor slabs and areas of high moisture. Here, it's the GPR. We're using it out here. This is the boring location. We found this boring location. There was no utilities there. You can see all the crack in the floor slab there. Again, you see the GPR going out there in the floor slabs. We just looking at the whole thing, picking up boring locations and look for areas of high moisture. Um, this is again more boring locations using GPR, making sure there's no steel here. There's some rebar here. Again, the rebar locations and the boring location here. We don't want to drill where the rebars are. More GPR, more picking up the boring location. More pictures of the GPR and rebar. Same. Boring location, cracks, steel locations. More GPR locations. This is the press machine with the GPRs on it to see where the steel was. So before we did the coring, of course, before we do the borings, we had to do coring out there to evaluate the concrete thickness and get a core samples of that concrete to see what's wrong with it. Why is cracking so much? Then we use our portable rig system. This is about 7 foot, 9 foot tall, and we did borings inside the building to a depth of 20 feet. Tried to anyway. Get soil samples with our portable rig. It's a gasoline operated rig. It has little fumes, but that's okay. So we measured the water levels in the holes after we did the borings. Let's see. I think he jumped up. Let's see if I can go back. Something jump up here. Okay. Anyway, we measured the water levels and there was no water. We backfilled the holes with the grout, basically a bentonite cement mixture. Um, we'll also install piezometers. Piezometers tell us where the water level is. Basically, two piezometers, piezometer PZ1 and PZ2. These are PZ1, PZ2. One of them was next to the oven. The other one was next to the press. Basically, it's a PVC pipe, 2-inch diameter, screen about 10 foot, and then above that is a regular PVC pipe. We put sand around the screen so that the water can flow, and then put concrete and bentonite above it to stop the water from the top coming into the air. So this measures only the groundwater. So piezometer PZ1 was near the press machine. PZ2 was near the oven. We drilled a hole at the location. These are the PVC pipe. It's about 2 inches in diameter. We put sand around it. And so that the water can flow. This is the cover of the piezometer. We measure the water level in the piezometer. We open up the cap. We put a tape measure in there with a weight at the end of it. We measured the water level. And we measured it at 2 different times in 2024, and it was always dry. There was no water in there. We also did elevations. Macro elevation was obtained to basically to evaluate the floor slab deflections, and it was done in accordance to Foundation Performance Association and Post-Tensioning Institute guidelines for the elevations. This is the Stanley water level measurements, and you can see the device. You put it on the ground, it measures the elevations. We did it throughout the whole 200,000 square foot building, all over the place. This is near the oven. This is near the press machine. This is the results of the micro elevation data. And you can see there are some areas 2.4, 2.4, 1.6, 2.0, 1.6, 1.0, 1.2. So you see elevations about a couple of inches differential, about 1.5 inches throughout the floor slab areas. 2.0, 2.8. So it's kind of not very uniform, and we feel like the floor slab was not poured level. That's why you see this change in elevations. This was not because of the presence of expansive soils. There are some expansive soils on the site, but not much. Vibration monitoring. As part of our work, we put like 8 geophones around the foundation system of the press machine that was vibrating. That's the press machine. These are geophones. We put them on the foundations of the machine and outside the foundation of the machine to see what the difference in vibration is and peak velocity. So we put one outside the foundation, one inside the foundation, one outside. These are the regular floor slabs. This is the press machine foundation. So we had 4 of them on the press machine and 4 of them outside. You see what kind of difference we get in vibration. These are geophones we put in there at various locations. That's the machine base. This is the actual foundation system for the building outside the isolation joint barrier for the machine. Again, this one is at the machine base. Little devices. We also did crack survey. We went out there throughout the whole building. We picked 40 biggest locations throughout the building. We measured the cracks. The length of cracks range anywhere from 2 feet, 26 feet, 25 feet, 32 feet. Some of these cracks were pretty long. They were hairline to about 0.1 inch in size. Here's measuring the cracking length, 2 feet here. There's the width of about 0.24, 0.04, 0.06. Here's another crack, 18 feet long. Here's another crack. These cracks were all over the place. You can see the cracks everywhere. Floor slab cracking, 18 feet. More cracks. That concrete was on this like a year or 2 years old, and it just had too many cracks everywhere. They spent millions of dollars on the building. They also had a forklift running around on the floor slabs, but apparently they were not going to use it anymore, and they didn't use it very much. Um, Here are the forklifts. And not a very heavy forklift, but he was picking up chunks of materials that they had on the site. This was outside the building. This forklift, they're using it outside the building. We did a bunch of lab testing, classification tests, string tests, proctor tests, compaction, density, concrete compression tests, swell tests, and petrographic analysis of the concrete, trying to see what's going on with the soil and the concrete on the project site. These are the boring logs here, B1, B2, B3, B4. We had concrete on the surface. Below that, we had fill, a couple of feet of fill, maybe 2, 3 feet, up to 4 feet. 4 foot of fill on the site. These are the borings inside the building, B1, all the way through B8. And B8 showed fill all the way down. That was in the area of the oven. Outside boring, B10, B11, B12, 13, they had some expansive soils there near the surface. Essentially, we had 0 to about 7 inches concrete slab. Maximum of the concrete slab thickness was 9.4 inches. From about half a foot to 16 foot near the oven, we had a big excavation, so they had foot. But in general, 0 to 4 feet was fill. And it was soft to hard, brownish, reddish brown, yellow, dark gray, basically lean clay. Then most of the other areas we had lean clay too. And outside in some areas, they had fat clay. Basically, the PIs of the lean clay was 16 to 30. The strengths were 0.23 to 2.5. So there was some expansive soils in that lean clay. Here's another lean clay, PI 7 to 28. Fat clay had PIs of 32 to 57. Looking at the boring logs, we had the concrete slab here in boring B1, 7.8 inches the concrete thickness. Below that, they had fill all the way down to 4 feet. We had below that, they had lean clay. The fill had a PI of 23. Below that, it had fat clay with a PI of 38. Below that, lean clay. The clay was as strong near the surface, and the natural clays were not that strong, 1,000 PSF. Here's a B2. Oh. One other thing on B1 is we checked the compaction in the fill. They all pass. Compaction was a 100% compaction, 99%. The compaction of the fill under the floor slab passed. Here's B2, all the compaction passed, 100%. And PIs were 17, 21, lean clay again. B3, all the compaction passed off the fill. PIs of 24, 32, 34. B4 in the building. All the field compaction passed. 100%. PIs of 26, 30, 25. B5, compaction, more than 95%. Again, we require compaction of 95% compaction on the floor slabs. Here is about 98, 99%. PIs of 19, 17, 25. Again, we require compaction of 95%. All the field compaction 0 to 4 feet, 100% passed. You know that lean clay with PI of 26. Here's another boring in here, fill 0 to 4 feet. PIs of 24, 23. All the compaction passed. You know that you got a lean clay PI of 22. Here we got concrete about 8.2 inches, boring B8. They have fill here, all densities passed, and all the way down. This is the one near the oven, which had a big excavation. PIs of 24, 24, 32, 32. D10. Again, these are outside borings, strong soils. Outside, it's not that bad. And PIs of 47, 57. Got some fat clay there. B11. Got a little bit of fat clay. PI of 27. Strong strength of 1,000 PSF. B12. Sure strength of about 12,000, about 1,000 PSF. PIs of 32, 27. This is an outside boring all the way to 25 feet. B13, you got again, PIs of 16, 26. Anything above 20 is considered expansive. And you can see shear strength of about 1,000, not very strong. We ran that PVR based on text.124E on the project site that indicates on the average how much heave you're going to have on this site. And the PVR underneath the floor slab areas based on the interior borings, not the exterior, was about 1.0, which is okay for an industrial building. So we didn't see heave as a major problem here. We also ran a swell test on the project with the applied overburden, and we saw percent swell maximum average about 0.11%, which is acceptable to basically less than 1 inch PVR. So again, expansive soils was not a major problem on this project. Since the soils are non-expansive, foundation system was adequate. So we felt like the foundation system with the fill was adequate considering the non-expansive soils. We ran Proctor tests for compaction. We had optimum maximum dry density 117, optimum 13%, PI of 17 on the fill. So this is a lean clay again, running again Proctor test. And in the fill, the PI of 20, 113, and optimum which of 14. Essentially, density for all the fill underneath the floor slab passed. We ran density tests on the cores we got on the concrete. We got numbers of 147 all the way down to 138. Typical concrete, you on the cores usually have a density of about 150 PCF, but the density on the concrete in some areas was low. Compression tests. We took these concrete cores, we cut the ends and cap them, put them in the machine, and start breaking them. The concrete crumbled and cracked. Various boring locations throughout the building. We broke the concrete. You can see pictures of concrete cracked all the cores we got, all the way from boring B1 through boring B8. We got compressive strings all the way from 4,990 to 1680. The design was 4,000 psi at 28 days. So we had some areas that concrete string failed. So we had some bad concrete here. We also did petrographic analysis of the concrete according to ASTM standard 857. So 856, we got a slice of a concrete core. We got the cores here. We think a little slice of it like that. We put it under the microscope and with blue dye, and you can see the aggregates all cracked up. Basically, the aggregates are granular material like sand, gravel, crushed stone mixed with cement. A lot of cracks in there. Yeah, we saw various things on the slides in here. The black is the cement paste. The red stuff is the aggregates. There's a void in there in the concrete mix. Here's another one. They got basically the brownish areas of fine grade mineral crystals chipped off, creating voids. Cement paste is ununiformly dense, covers fine particles. The blue circles on the left shown is entrained air. So looking at it, the aggregate was chert here, surrounded by porous paste. The tempered concrete showing porous paste. That means that the concrete had a lot of water in it, and they had water added in. Poor quality aggregate was used on the project. There's a shortage of aggregate, so they were using aggregates that was not high quality on the project. Engineering analysis, we look at the aerial photos, we look at the topographic map, we look at the elevations, floor slab cracking, vibration, field compaction evaluation, and presence of perch water table under the foundation system. We look at moisture profile and liquidity index, review the rainfall data. We look at the GPR data. We look at the concrete core densities and concrete steel placement. We look at the evaluation of a concrete floor slab strength, controlled joint evaluation, slab thickness evaluation, petrographic analysis of concrete samples, recommendations on concrete slab thickness, and settlement analysis. Looking at aerial photo, the area was as flat as a pancake. It was out there. There was just no topography. It was a good site. There was nothing on it. No ponds, no excavations. Start working on it in 2022. Starts clearing it. This is the topographic map. Shows no elevation change. We look at the elevations on the project based on PTI, Post Engineering Institute, to see if the floor slab elevation is out of code. Here's some definitions. Deformation is a change in shape of foundation after the original foundation construction, called deformation. Deflection is a maximum deviation from a straight line between 2 points. Deflection divided by horizontal distance over which the deflection occurs, called deflection ratio. So deflection ratio is basically the deflection divided by horizontal distance over which the deflection occurs. Here's the points 1, 2, and 3, and here's the deflection on the slab. This is not right. The deflection between 1, 2, and 3 is not this. It's this. It's much smaller. There's another concept called tilt. Tilt is basically a planar rotation measured over the length of or width of the foundation. So if you got a rigid slab that moves, this is Y is a deflection over the distance. It's called Y or X, called tilt. TRCC, Texas Residential Construction, and ASCE, they say basically up to 1% tilt is acceptable. There's another concept called slope, which is differential elevation between any 2 points divided by horizontal distance between them. So we say typical acceptable criteria for floor slab here is L over 360, which is in 1 inch in 30 feet in deflection. Looking at the elevations of the floor slabs in here, we had some cross sections. We'll look at the C. This is BB, AA. This is AA, BB, CC. We just ran some cross sections, and DD. And look at the floor slab deflection and check the criteria. And we got deflections L over 706, L over 835. Which one's the deflection ratio was real small, less than 1%. So it all passed. Tilt was 0.07%. It passed. Here's another point. Basically, this is the BB section. Looking at the floor slabs movement. And we measure the deflections. L10, anything above 360 passes. And tilt was 0.06, 0.01%. It passed. Again, this is section CC. Looking at the deflection of the floor slabs. L over 1930, 1971, 23. Anything greater than 360 passes. And 0.01 tilt, which is less than 1%, passes. This is DD. That's a floor slab deflection here. And we measured the deflection 1, L over 474, 73, 510, anything above 360 passes. Tilt was 0.12%. Passes. So section AA, BB, CC, DD. Look at these sections. Deflection, they all pass. Tilt, less than 1%, all pass. Floor slab crack survey. Again, we ran all kinds of crack sizes here. The width of it, 0.06, 0.01, 0.04, and some of the crack width of the floor slab cracks. Again, here, right here, 0.06. Length of the cracks. You can see all the way down to 40 feet long, some of these cracks. TRCC's got requirements for floor slab recommendations. That's Texas Residential Construction Commission that talk about the crack sizes. They're not in business anymore, but they give guidance on all of the crack sizes. Floor slabs 1/8 of an inch, flat work 1/4 of an inch. Maximum flat work separation, expansion joints 1 inch, stairs settlement 3/8 of an inch, sheetrock 1/32, brick 1/8. So that's just something to compare to. Vibration evaluation. We had this machine, press machine that was vibrating, and we look at the peak velocity in the geophones, and it's the peak velocity and frequency. So looking at the NAFAC, and it's got about the dynamic and allowable movement, vibration. Looking at the frequency and peak velocity, that's where we came up with. We had a peak velocity of about 0.258 inch per second. And here, of course, frequency of 50.05 CPS, cycles per second. It puts us at near severe to persons. In other words, the vibrations of that press machine was severe, but caution to structures and danger to structures. The vibrations was below the limit that was a danger or a caution to structures. It was severe to persons, but this was not detrimental to the foundation system. So the vibration considered to be acceptable. Compaction evaluations. We check all the compactions in all the borings. They all passed anywhere from 88% to 100% compaction, and so he passed. Perch water, there was no perch water underneath the floor slabs. Water just was no water. Soil moisture profile, the red ones is the in situ moisture. The green and blue one is from TxDOT 124 PVR, the wet conditions, and also the dry and the dry conditions. And you can see the moisture in boring B1 inside the building was pretty dry. Was below the wettest condition and the driest condition. It was pretty dry. And again, B2 was pretty dry. B3 was pretty dry inside the building. B4 was real dry. Again, this is the wet condition. This is the dry condition based on PVR method, TxDOT 124. And this was below that. And you can see boring B5, the moisture was kind of like close to the dry condition. B6, close to the dry conditions all the way down. B7, dry conditions. B8, a little bit on the wet condition, but the rest of it was, dry. Moisture content B10, boring B10, dry. Again, we're looking at boring B11. The red areas are dry. B12, kind of like average near the surface, then becomes dry. B13, kind of near wet, near the surface, then dry. We'll also look at the liquidity index. Liquidity index tells you basically how far the natural moisture content, how much the in situ moisture is between the plastic and liquid limit, essentially as a percentage. So we measured the liquidity index on the site. Anything above 0 means the soils are wet. Anything below 0 means the soils are dry. So this is the exterior boring, and majority of the soils in the exterior boring show they were kind of a dry soils. The moisture contents were dry. And these are the interior borings, all the borings. Again, anything above 0 is wet. Below 0 is anything above 0 is dry. Is wet. Below 0 is dry. So we see most of the data points for all the interior borings fall along the dry side. So the soils underneath the floor slabs were dry. However, they were not heaving up. They were not that much expansive soils. We looked at the rainfall data. The building was built in 2022, 2023, and the average rainfalls 2022 was 36 inches. 23 was 41 inches. So average rainfall in Houston is about 50 inches. So both years, the rainfall was not very significant. So that was not an issue in the construction of this thing. GPR, we checked out the GPR throughout the whole floor slabs and the boring locations. We ran GPR on the slabs, and near boring B1, for example, we found in the area where the boring was, average of slab was 8.5 inches. Rebar was at 4.5 inches. Was supposed to have been 3.5 inches. And the slab's supposed to be 7 inches. Spacing was 15 by 15. Spec was 15 by 15. That's boring B1. Boring B2 again, slab was 8.5 inches. The rebar was almost 6 to 7 inches below grade, below the top of the concrete. That's not good. And the steel spacing was 15 inches, which is fine. Specs call for the steel placement at 3.5 inches. Here's was all the way at the bottom, 7.5 inches. Here's boring B3. Slab was supposed to be minimum 6 to 9 inches thick. It was supposed to be 7 inches. The steel was 4.5 to 7.5 feet deep. It's supposed to be 3.5 inches. B4. The slab was 7 to 9 inches. The rebar was 5.5 to 6.5 inches below grade, below top of the concrete. supposed to be 3.5 inches below the top of the concrete. The slab was supposed to be 7 inches. Here's another GPR data. Concrete thickness was almost 10 inches. The steel was 5.5 to 7 inches down. Again, it should have been 7 inches, 3.5 inches. Depth, D6. Concrete was 7 to 8 inches thick. And the steel was 3 to 5 inches deep, which is okay. D7, 7 to 9 inches concrete thickness. 4 to 6 inches below the top of the concrete was the steel. It's supposed to be 3.5 inches. D8, concrete was 7 to 10.5 inches in thickness. And it was 4 to 7 inches below grade. Below the top of the concrete is supposed to be 3.5 inches. So these are the GPR scan areas in the floor slabs. And looking at some of these scan areas, we've seen the scan, this green area indicates potential for void or changing the property in it about 3 to 5 feet deep in the soil. Here's another scan area of the floor slab using GPR. Showed somewhere about 2 to 4 feet potential void or change in soil properties again. Here's another scan in the floor slab area. And here in the pink area indicates below the concrete slab, there's a separation between the soil and the concrete floor slab. Here's another scan area of the GPR. Again, the red arrow. Basically, the pink area indicates a void beneath the concrete slab. So looking at this GPR areas throughout the floor slabs, there are some indications of maybe there is some anomaly of potential voids in the soil. And here's another one. The green area indicates potential void with changing properties of the soils at a depth of about 3.5 foot below the pad. Here's another GPR area. That's a GPR location. That's about 3 to 4 feet, 5 feet. This area indicates potential void. So here's the GPR again on this location here. This area indicates anomaly, potential void at the depth of 4 feet. So GPR at various locations indicates potential void and things like that. Here's another one. GPR value here. The pink indicates potential void. Concrete cores density. Again, we measured the density in these cores. We got as low as 138. We like to have 150. So density didn't meet requirements. Concrete steel locations. When we core the slab, these are the cores, the steel in there. Here's at 6 inches below the bottom, near the bottom of the core. Here is the 6.5 inches where the steel is. It's supposed to be 3.5 inches deep. Here's the core at 7 inches, the steel location. Here's the core at 7.5 inches. Here's at 5 inches. Here's at 5.5 inches. Here's at 6.5 inches. Here's at 7 inches, 6.5 inches, 7 inches, 4 inches, 4.5 inches, 5 inches, 5.5 inches, 6 inches, 6.5 inches. So it was supposed to be 3.5 inches from the top of the concrete. So we saw this concrete steel location was near the bottom of the concrete cores. Concrete floor slab strength. We measured them all the way. Supposed to be 40,000 psi, 28 days. We measured 5,000, 4990, and we got 2,500 all the way down to 1680. These are concrete cores we broke. ACI says concrete represented by the cores are considered to be adequate if the three cores equal to at least 85% average of them of F prime C, and no single core drops below 75 F prime C. So looking at these cores here, the design was 4,000 psi, 75 C, nothing should drop below 3,000. Average of the three cores should be 3,400. So concrete here based on ACI fails. Control joints, again, we do control joints. We saw cut the floor slab 4 to 12 hours after the pour. We saw cut them like that. This is the floor slab. You saw cut them like that to tell the concrete where to crack with the saw cut. We saw cut 1/4 of the floor slab. If the floor slab is 7 inches, you saw cut 1.7 inches. It tells you what the concrete cracks below it. So when we look at the control joints in here, they were like all the way down up to about 25 foot in spacing. And if you look at the control joints, basically tell the concrete where the cracks and controls cracking of the floor slabs. And ACI talks about the thickness of the control joints should be anywhere around 14 to 21 feet. We recommend the control joint of 15 feet on this site, and we found control joints as much as 25 foot spacing. The control joint depth should be about 1.75 inches. We found many locations the control joint depth was 0.25 inches. So the control joint placement in the floor slabs was inadequate for crack control. Slab thickness recommendations. ACI says the floor slab should not be thinner than 0.25 inches of the design and thicker than 3/8 of the inch of the design. So if your design is 7 inches, it should not exceed, it should be in the range of 6.5 to 7.38 of an inch, which floor slab thicknesses, went all over the place. So it doesn't meet ACI 117. Petrographic analysis, when we look at the aggregates on this thing, they use cheap, weak aggregates, weathered limestone aggregate used with other inferior aggregates such as chert, mudstone, and weak aggregate in the mix. They couldn't find good aggregates, so they used chert and mudstone as aggregate, and they used basically weathered limestone. And they added a bunch of water during the construction called retempering. So retempering is a process of changing consistency of the concrete by adding water and remixing. Recommendations for the concrete slab thickness. There was a forklift out there on this thing. We checked the forklift. If they use the forklift a lot, 7-inch concrete is not adequate. They use on this project. So these forklifts were picking up these countertops that were heavy. We ran the design value based on PCA, Portland Cement Association, on the forklifts, the axle load, forklift wheel spacing, number of wheels, axle, stress, and went to the chart that's got the stress on per 1,000 pound, axle load PSI, and then we had the wheel spacing. Based on that, we determined that the floor slab really should have been 10 inches if they want to use forklift on this site. So they said they didn't use the forklift very much, so I said, well, then 7-inch concrete is adequate. Sediment analysis, where we look at the building, in the floor slab, there were these heavy materials were stored. We checked the contact pressures, and there was about 600 PSF. We ran the settlement, it was not a big deal, so the settlement was not an issue. Reasons for foundation distress. It was basic as a result of poor construction, poor quality materials. These are the two reasons why it failed. Poor construction, faulty construction result as a function are indicate presence of many cracks throughout the floor slabs. Cracks are lots of cracks. Examination of the floor slabs indicate rebars were located all the way down on the concrete floor slabs. Essentially, rebar was supposed to be at 3.5 inches. It was not there. And so reinforcement was totally in the wrong place. Control joints was supposed to be about 15 feet. They were as much as 25 foot spacing. So that's improper control joints placement. The cores were 6.6 to 94.1 in thickness. It was supposed to be in 7 inches. So it doesn't meet specs for ACI. Poor quality material. We ran all the compression tests on the concrete. It's supposed to be above 4,000 PSA, and the concrete values was as low as 1,850 PSI. Petrographic analysis indicates they used wrong aggregates, cheap aggregates, whether limestone used, chert and all that stuff in the concrete. That's why it was so weak. They added a bunch of water to it during the construction. So that caused a lot of problems. Repair techniques. In terms of repairs, we recommended 2 things to do, which the first option really is not a very good option, but you can use a crack repair using stitching method. It's basically you put these devices in there. Essentially, it's basically called crack repairs option. It's basically a risk of foundation distress compared to higher others. Involves drilling holes on both sides of the crack, grouting the stitching dogs, U-shaped metal stuff. You put them in there, you grout them in. There's just too many cracks to do that, to do stitching. But if you want to increase the life of the slab, you could do that. Do the stitching and grouting it. You cut a groove and stuff like that, and stitch it. The purpose of you put sealant in it in the cracks. Of course, you don't want the water getting in there. Basically, all the repair and the stitching should be in accordance to ACI 224. You can also use carbon fiber for the crack. They use a lot of carbon fiber for crack control, which is pretty good. Level 2, we say recommend it. Remove the existing paving, put a new 7-inch concrete slab in there, and build it in accordance to ACI requirements. Questions? Apparently, these guys went out there to the contractor who poured the concrete and also the concrete supplier and got some money out of them. So that was an interesting project. Lots of interesting data that came out. We had to get them all that figured out. I want you guys. I'm doing a poll here. See how